we're given a solid, and it's formed so that for the region x going from -1 to +1, y goes from 0 to 1 minus x squared in the xy plane. You take that and you take any cross-section of the solid perpendicular to the x-axis. Well, that cross-section is a circle where the diameter lies in the region. And the question, find the volume of the solid. Now, in case you're wondering what's the diameter of a circle is a line segment connecting opposite points of the circle. So the solid will be half above and half below the xy plane. All right, so we have 4 options. And does anybody have the answer? Or does anybody like to say, aha, I think it's this? You have a 1 in 5 chance. B. Interesting choice. Not B. Now you have a 1 in 4 chance. Your odds have improved. What? A. Another good choice, because it's right. So the answer is 4 pi over 15. Okay. Now I will say 16 pi over 15, option C, is very tempting. We'll talk about why it's tempting. So here's our region if we look at it from above. We're going from -1 to 1 in the x direction, and 0 to 1 minus x squared. Now, this is if we look directly from above. If we look at it sort of from an angle, we see our plane, and then we're taking a slice perpendicular to x. Now, when we slice, we're going to get a piece of our solid, and that's going to be a circle. All right, so there's our slice. If we look at it and pull it to the side, we see, aha, we see our cross-section is a circle. And this length here corresponds to that length there. Now, what's that length? Well, it's the distance from 0 up to the curve. So it's 1 minus x squared. Now, that's the diameter. Now, for diameter, we're usually more interested in radius. That's half the diameter. So the radius of our circle is 1/2 1 minus x squared. So now we are ready to go, because we say, look, we have a circle, we have its radius, we know how to find area. And volume is the integral of area times width. So area is pi radius squared. The width, we're slicing with respect to x, so it's dx. And then from there, it's mostly just algebra. You square a half, that becomes a fourth. You can pull out the pi in the fourth. Square 1 minus x squared, 1 minus 2x squared plus x to the fourth. Here, I'm using the fact that this is an even function, so there's symmetry. So I can go from 0 to 1 and double the answer. And I just like 0. 0 is a friend. 0 is a very useful number. Well, integrate, evaluate, and simplify 4 pi over 15. Why is 16 pi over 15 very tempting? If you forget the half, you would have gone 16 pi over 15. That's what it worked out. Now, I guess a quick question. Is this a volume of revolution? And why not? All right. So is this a volume of revolution? That was my first question. The answer? No. Now you might say, well, wait a second. All your cross-sections are circles. Isn't that what happens for volumes of revolution? It is true if you have a volume of revolution that you get cross-sections that look like circles. So why isn't it a volume of revolution? If you have a volume of revolution, what's true about your circles? And in particular about the centers? They go along the axis you spin around. Now, if you look at this, what happens is that your centers are actually sort of halfway in between. So there's where your centers of your circles are. So it's not quite a volume of revolution. But there is an interesting idea called Cavalieri's principle. And Cavalieri, Italian mathematician, said, look, I can just sort of move things around and treat it like it was a volume of revolution. But that's a different story. All right, so there we go. First problem done. Good. We'll have more. And the more you practice, the better you get. All right, so now our next thing, of course, our thought for the day. Know the difference between being active and being productive. A lot of people, they stress on, they say, I am spending so much time for this class. Why am I struggling? Well, sometimes what's happening is, yes, you're spending time, you're being active, but you're not being productive when it comes to your learning. So you need to think about, how can I go and say, let's improve on the time I spend. So in other words, it's not always about quantity of time, it's also about quality of time. And you're probably thinking, okay, well, since you said know the difference between being active and being productive, what is it, Steve? Well, here are some thoughts I have. So first off, there is an overlap. You can't be productive if you aren't being active. But there's something more to it. And it's sort of saying, what are you putting into it? So here are some characteristics I thought of which correspond with being productive. Namely, you're intentional. When you come in, you have a plan, you know what you're going to do. You don't just sit down and just say, I'm going to wander aimlessly. You're focused. You're not distracted. It's so easy to be distracted. There's so many distractions now in the world. You say, look, no, this is my time to learn. I'm going to invest in myself. I'm going to put distractions to the side. And it's good to be able to build up to the point where you can say, I can be focused for 75 minutes doing calculus. Now you might want to say, that's an oddly specific number, 75 minutes. Why did I pick 75 minutes? That's the length of the exams. Yes. So you want to be able to actually do math for 75 minutes in a row. Because if you can't, those exams are going to be really tough. So practice that. Challenge yourself. Get out of your comfort zone. If you're not being challenged, you're not growing. You have to have problems that you struggle with. Now, you don't want problems that you can't do, but you want problems that you can barely do, that really test you and really stretch you. You might say, well, where can I find such problems? Well, the good news is we have lots of old exam problems available for you. And, for example, look on the back of your handouts. And really, this is not so much how you make things productive, but how you know you're being productive, is that once you're done, you're better than you started. You know, you've made progress. It's hard to tell the difference between a good student and a bad student watching them for a day. They'll look the same. Now, of course, I know you're all good students. But how do you tell the difference? It's what happens over time. A bad student will spin their wheels and not make progress in their education. Whereas good students, they may not make a lot of progress on any single day, but it's incremental. They build up. And as you'll learn later in the semester, if you add up lots of little tiny terms, you can get very big. You just have to persist and keep going. All right, so that's a thought for the day. Don't worry, they won't all be quite so long. All right, so let's remember what we're doing. What are our goals for today? Well, we're going to talk about finding volume again, but this time by adding up shells. So we're doing shell method, and we have a formula for that. So in particular, if you're following along with your formula sheet, this is today. We're doing that formula for volume. All right, and we have another method that we talked about, the disc washer method. And so we're going to talk about the two and compare them and say, how do they relate to one another? How can we understand when to use which one? So that's our goal. Before we do that, we should finish with last time, because I do want to get a little bit more practice with the disc and the washer method. So here we go. So this is from last time. We haven't gone to our new method yet. So let R be the region bounded by y equals 2x and y equals x squared. So I'm going to sketch that really quickly. What does y equal x squared look like? blah. That's cool. So here's our y equals x squared. Y equals 2x is a line. And so we have our region. It's the region in between the two. We'll just shade it. So here is our region bounded by these two curves. All right. And with a little bit of work, doesn't take very much, you can find that the intersection happens at the point x equals 2 and y equals 4. All right, so there's our region. Set up, but do not evaluate. And I will say these are 3 of the favorite words of students in Calc 2. Do not evaluate. Because we don't actually have to carry out the integral. And I will tell you, a lot of the first exam is setting things up. And historically, we've had exams where you could get an A and not even know how to do any integration as long as you knew how to set things up on that first exam. Now, I don't know what's going to happen with this exam. You should know how to do integration, but a lot of the focus is on setting things up. Okay, so we want to set up our integrals, define the volume. When our region R is rotated, we have 2 options here. Around y equals -1, and then around x equals +2. Now at this point, we haven't learned any methods other than last time. So we see rotated around. When you see rotated around, that means we're doing a volume of revolution. So here, this is our secret code for volume of revolution. Now, after today, we have to come to a decision about how we do it, but at this point, we don't have a decision to make. We say, all right, volume of revolution means that we're using our formula. So we're adding up A to B, pi, big radius squared minus little radius squared times your width. Now, where did that come from? Well, came from our lecture last time, but it's also here. Someone's like, what? They want us to know things. That's right, we want you to know things. Okay, so, well, 2 problems to do. Let's start with A. Okay, and I regret putting that there. So, okay, I'll just put it here, A. All right, where are we rotating around? We're rotating around y equals -1. So we dash here. Here's y equals -1. And we are spinning. All right. So in this case, when we spin, we're going to end up forming a solid. Now, what should we integrate with respect to? X or y? X. X. Why X? Well, think about, you have 2 ways to slice. You have a vertical slice or a horizontal slice. And the question is, what, when you spin, makes the right shape? So washer method, it needs to look like a washer. What's a washer? It's essentially, it looks like you take a circle and you punch a little circle out, but it has just a little tiny bit of width. Very thin width. This is what a washer looks like. So we need to form that shape. This is our washer. So we need to take a vertical slice, which means we're integrating with respect to x. All right, so now we know we have some information. So we're going to integrate. What are the bounds going to be? Where do you start? Where do you stop?
Your big one's going to be from the x-axis to the y equals x squared, right?
Well, we're talking about these bounds.
Oh.
Where do we start x? Where do we stop x? I'll give you a hint. I'm kind of pointing.
0 to 2.
0 to 2. Yes! Woohoo! Pi. I know how to do that. That's called pi. Okay, now, big radius. So be careful. It's not going to be 2x. What will it be? Well, it's this length here. It's from the furthest curve out to your area you spin around. So what's the distance from y equals 2x to y equals negative 1? How far away is that? 2x plus 1. Now you could also think of that as 2x minus 1 if you like. And since we don't have to actually evaluate it, I'll write it in that way. Just emphasize you're taking the difference. What's your small radius? Well, it's from the near curve to where you spin around. So what is that going to be? So x squared, again, minus 1, or x squared plus 1 squared. And then the width? dx. Okay, so that's part A. We made it. Woohoo! Because all we have to do is set it up. All right, any questions on that one? No. Yes?
Can you just explain, like, why is it minus 1, but not just plus 1?
Well, it is plus 1.
Right, but like, why do you want to kind of keep this notation, like minus 1?
Well, just so people say, where did the plus 1 come from? So what you're really doing is you're looking at differences. And so you're saying, how far apart are they? And so sometimes people are like, well, where's that plus 1? How do I figure it out? It's always, take the difference between the two.
Distance is like absolute, so we want just absolute value of...
Well, you could think of it as absolute value, but you're squaring, so it doesn't matter. So, do you have another question?
So, when you picked which curve to pick as your first one, or which one was farthest, did you kind of look at it as like y equals 2x is like above y equals x squared, and therefore that makes it the farther one?
Not necessarily. So which curve is farthest? Well, think about where you're spinning around, and just say, which one is closer to where you spin, which one is farther from where you spin. Now, I'm spinning around y equals negative 1, so the farther curve is y equals 2x. What if I had spun around y equals 5? Now, which one is the far curve?
Right.
The x squared is, the near curve is 2x. So it's in relationship to where you're spinning. That's how you determine which one's near or far.
From the area, like, is it possible to have a case where, depending on where you, on your interval, depending on where you choose to start counting, sometimes the closer one will be one function, and then sometimes the closer one to the x will be another function?
Yes, we'll talk about that. We'll see one later on. That just means more work. More, not the L'Hopital kind of more work, but more work. Okay, so we have a part B. Okay, part B. Now, around x equals 2. So here is x equals 2, and we're spinning. So we're going to end up forming a shape. Now, in this case, what should we integrate with respect to? Y, right? Because we think about which one of these would form the right shape. So it's this kind of horizontal slice would form the right shape. Horizontal slice means integrating with respect to y. Okay, so we have our integrating with respect to y. All right, now that we figured that out, we say, okay, go through the formula. We have an integral. What will the bounds be? Where does y go from? 0 to 4. Pi. Okay, now we have to pause for a second and say, whoops, we have these as y's as function of x. We need to change it x as functions of y. So this y equals 2x, what's another way for us to write that? As x equals 1/2 y. Divide by 2. Y equals x squared. What's another way for us to write that? x equals square root of y. Now you might say, well, don't you need plus or minus? Well, we just need the plus because we're staying over on this side. The minus is over on that side. All right, so x is equal to the square root of y. All right, now we're ready. Okay, so we are looking at this and we're trying to decide which one is our big radius. So we're in relationship to where we spin. Which curve is the farther curve out? The line or the parabola? The line. So our big radius is coming from here. So we need to figure out what's the difference from x equals 1/2 y to x equals 2. So what is that difference? That's our radius. 2 minus ½ y. Now why didn't you say 1/2 y minus 2? So why is it 2 minus ½ y, not ½ y minus 2? Well, because which one is bigger? The 2 is bigger. It's large value minus small value. Okay, subtract our inner radius. Okay, that's the other curve. What's that distance? 2 minus square root of y. And then we square. Final thing, dy. Don't forget the dx or the dy when you're writing these terms down. They're important. They're a definite part of the answer. And if you don't include it, you lose points. All right. Any questions? Good. Well, let's go on to the other idea. So we've talked about washer. Now we're going to do a volume of revolution, but in a slightly different way. So we have a similar picture. We have a region. We are spinning it around a line. So it's the same setup as what we just talked about. But the thing that's going to be different is how we figure out the answer. So what's going on? Well, we're going to cut our region up into strips. It's the same thing we did before with washer. However, if you think back to washer, our strips were perpendicular to the line we were spinning. Here, they're parallel. So what happens is when we spin, we're not forming a washer shape, we're forming a different kind of shape. So what does our shape look like? Well, the answer is it looks a lot like a cylinder, because essentially it is. It's a thickened cylinder, and we call it a shell. So you say, okay, well, we can approach it philosophically the same way. All we have to do is figure out what's happening with one shell. If we can figure that out, then we add them all up, and life is good. So once we figure out the volume of a shell, then to find the total volume, you add up. So remember, that's integration. Well, we have to figure out the volume of a shell. So let's do that. So we'll start with the shell. It's our thickened cylinder. You know, pull out from your pocket a pair of scissors, and we start cutting. Okay, so now we've cut along the side. Okay, so we've sliced one side, and we can grab the sides and lay it flat. So we're taking the shell, laying it flat. And now we have a shape that looks like a box. Like, hey, we know how to handle these things. And we say, all right, so what's going on? Well, we have here a measurement. That's going to correspond to this measurement. We'll call this our height. So we have our height. All right, that's part of our box. Now, we also have another measurement that's pretty easy to identify. And this measurement here, we'll call this our width. So it's up here, this is our width. So the last part, that's the one we need to think a little bit about. It's not going to be too bad. I don't want to make it sound super mysterious. But what is that length? You can think of it as circumference. Right. It was what you do if you would go all the way around. So that's your circumference. Now, this is circumference of a circle. What's another way to say circumference of a circle? 2 pi radius. Good. 2 pi times your radius. All right, so now what's the volume of our box? Well, we just multiply these things together. So 2 pi times your radius times your height times your width. And there we have our shell. Now, is it exact? No, it's an approximation. However, as your slices get smaller, approximations get better, and the approximation squiggly lines flatten out and become equal. Okay, so coming back here, what's our volume? It's 2 pi. Radius, height, and width. So that's our formula. Now let's put all of these in the picture. Okay, so radius, what is that? Well, it's from your slice to where you're spinning. So this part right here, that's your radius. How far is your slice from the line that you're spinning? What's the height? Well, the height is this measurement. The length from top to bottom. Is that showing up? It's kind of showing up. Okay. And finally, what's the width? So this little piece right here, that's your width. So this is usually your dx, your dy, depending upon what you're integrating with respect to. Now, by the way, let's notice something. We're after a volume. How do you usually find volume? If you think of it like box, like length, width, height, you're multiplying 3 measurements of length together. So you should expect to say, well, are there 3 measurements of length? Radius is a measurement of a length. Height, that's a measurement of a length. And width is a measurement of length. So it's like, oh yeah, the units work out. And that's sort of a sanity check. Are the units doing what they should be doing? All right. Any questions? Well, let's try it out in practice. Okay. Find the resulting volume when the region x goes 0 to 4 and y goes from 0 up to root x is spun around the y-axis. So I'll note that this is y equals root x. And in case you're wondering, square root of 4, true story, it's 2. Okay. Well, what can we do? We have choices. Which method do you want to use? What? You want to use the disk method? We just got a shiny new toy, and you're like, I don't want to play with my new toy. Give me the cardboard box. Okay. All right. All right. Let's go ahead and do the disk method. Now, if we were going to do the disk method, here more appropriately would be the washer method, what kind of slices would we be taking? It'd be horizontal slices. So if we were doing the washer method, what we would have, so we'd use horizontal slices because that would form little washers. Okay, so the washer method says the volume would be the integral a to b pi, I'll shorten this as big R squared minus little r squared width. Now, we have to think about this. We're doing horizontal slices, so we're integrating with respect to y. Okay, so that's telling us our width is going to be our dy. What will our bounds be? We're integrating with respect to y, so we need to have y bounds. Where does y go from? 0 to 2. These are y bounds. Pi is pi, and now I regret the amount of space I gave myself. Okay, what's our big radius? So we're going from where we spin to the furthest one out. What the big radius is? 4. Right? That's the furthest thing out. So 4 squared. What's the inner radius? Y squared. Okay, so what's the distance? Well, it's y squared, right? Y squared to 0. So it'd be y squared squared. All right, great. Well, we could probably integrate that. Now, 4 squared is 16. Integral of 16? 16y. Remember, we're integrating with respect to y. Y squared squared is y to the 4th. Integral of y to the 4th? Y to the 5th with a suspicious gap, which we put 1/5. Evaluate 0 to 2. Okay, 16 times 2? 32. 2 to the 5th? Powers of 2, 2, 4, 8, 16, 32. Who doesn't love their powers of 2? Okay. Now, if you get a common denominator, 32 times 5, 160. Yes? No? Maybe? 160 subtract 32 is 128. So we got pi times 128 divided by 5. Okay, now that's the old way. Let's do our new way. It's a whole new day. Suppose we're like, I want to practice the things we've learned. Shell method.
We just did, though, technically.
Yeah, but even more. Really lean into our education. All right, so if we're doing shell, it's not going to be our horizontal slices, so that leaves us vertical slices. What are we integrating with respect to? X. All right, so we have AB 2 pi, radius, height, and width. Okay, so dx. What are our x bounds? 0 to 4. 2 pi is 2 pi. Now, what's the radius? How far are we? So think of this as just sort of a generic x as our slice. How far is x from the y-axis? It's x away. So times by x. Okay? Now, what's the height? Square root of x. And okay, so square root of x. Oh, just barely had enough space to write it. All right. Whew. Good. All right. Now, of course, we can simplify this. 0 to 4, 2 pi, x times square root of x, x to the 3/2. Okay, so what's the integral of x to the 3/2? Yeah, x to the 5/2, and as I also heard someone say, 2/5. Don't forget to, you add 1 to the exponent, that's how 3/2 became 5/2, but then you have to multiply by the reciprocal. evaluate from 0 to 4. Okay, so 2 pi times 2/5, that's 4 pi over 5, and times 4 to the 5/2. Now that's not too bad. We just say, great, 4 to the 5th, which is 1,024, right? Yes? And then you take the square root of that. Square root of 1,024 is 32, right? Now, I see some people who are skeptical here. You would never do it that way. Be smart. When you're raising something to the 5/2 power, you think of it as there's two things. Raising to the power 5, raising to the power half. So if raising to the power 5 makes it big, raising to the half makes it small. Make small first. So 4 to the 1/2 is 2. See, that one you can do. 2 to the 5th. And then you just, that's your fingers. 2, 4, 8, 16, 32. So we get 4 pi over 5 times 32, which is equal to 128 over 5 times pi. Now, do you notice anything about our two answers? They're the same. Why do you think that happened?
Coincidence, because you cheated.
It's not coincidence. I didn't cheat. It's because we're measuring the same thing. We're just measuring it in two different ways. So we can't get two different answers. All right, so some quick comments about washer versus shell. You can use either method. And there are cases where it makes sense to use one or the other. When you can use both methods, you're going to get the same answer. Now, how do you make a decision about which method you can use, or which method you should use? Well, look at how the problem was phrased. And you think about, okay, how is the boundary of the region expressed? So if they give you y as functions of x, you say, well, let me think about doing it with respect to x. Sometimes you can't get from y as a function of x, x as a function of y. In other words, you can't find those inverse functions. And then you're forced to use a particular method. But I tend to be of the mindset, let me just try with the way it's been given to me. Another thing is think about which method minimizes the number of integrals I need to do. Now, this was raised as a question earlier. Well, what happens if you have your function changing, your boundary curve changes? The answer is you have to split your problem. And you say, well, I'm going to find my answer by doing it in multiple parts. So every time a boundary curve changes, you have a new integral that's going to have to be added in. So you want to say, I want there to be as few integrals as possible. Now, I have a little table here which says, well, you can either do vertical slicing, which means you integrate with respect to x, or horizontal slicing, which means you integrate with respect to y. And again, you can rotate around a vertical line, or you can rotate around, well, this is rotating around a vertical line, or you can rotate around a horizontal line. And you see that you'll get different methods. Now, when in doubt, just say, let me take a slice and spin it. Look at what the shape looks like. The shape will tell you what method you're using. All right. Well, I've been doing a lot of practice. Any questions? Okay. Well, in that case, here's a problem. The region in the first quadrant, bounded by y equals root x, this curve, and y equals 2 root x minus 3, which is that curve, and I've marked some various points here, is spun around the line y equals 2. Use the shell method to find the resulting volume. Maybe let's talk about the setup. So here we have our updated picture, right? Because we should write things in terms of x because we're going to have horizontal slices. All right, so we're going around y equals 2. What's the radius? Because I think that might be the one that is most tricky. How do you find it? It's marked here as radius.
Y squared.
It's not y squared. It's not quite y. 2 minus y. Because you're going around 2. So the question is, how far is 2 from y? Well, it could be 2 minus y or y minus 2, depending upon which side you're on. But we're below the line, so it's 2 minus y. So our setup, integral 0 to 2, because those are the range for our y values. We're slicing in the y direction. Radius is 2 minus y. Our height, we can now think of that as our dy, and our width is the length between the two curves. So that's the setup. I hope you got that far. All right. How do you finish it? Algebra. Algebra. Okay, so you combine the y squared terms. I pulled out a 3/4 just because I've had bad experiences with fractions. So I like to avoid them when I can. Now, 2 minus y times 4 minus y squared, if we want to integrate that, what do? You integrate it. Distribute. Multiply out. And then you integrate the individual terms and you evaluate. So the answer was 10 pi. Quick side note, at the end of today, if you were to have done this with the washer method, you'd have to do 2 integrals because you have a change in the boundary curve. Every time you change a bounding curve, you have to add an integral.